Okay, hi. Welcome to topic 3. This topic is sequences and series of functions. So here it's about the types of convergence of sequences of functions, and also some theorems on series at the end. So we'll actually start by going through boundedness, which is a topic from metric spaces. So that's part 2. And we introduce it here because it's not really used in any examples in metric spaces. And well, it's not really used in anything here either, but we do talk about bounded sets, bounded sequences, and bounded functions here. So here are the 3 equivalent definitions for boundedness. So what this means is that we can prove that all of these imply each other. And it's quite intuitive as to why these all talk about boundedness. And here, if the whole metric space satisfies one of these properties, then we say the metric space is bounded. Okay, now let's move on to convergence. So there's like 3 types of function convergence we did in this course, and I think most people will be quite familiar with these after assignment 3. But let's quickly recap. So the first type is pointwise convergence. So pointwise convergence is at every point the sequence of function values converge to some number. So the example here is tan inverse of kt. So tan inverse looks kind of like this, with asymptotes at pi on 2. And as we increase k, the slope here gets steeper. So we kind of end up with a step function almost. And we can show that for any single point, we can take k large enough so this point can be as close to this function as we want. So here is pointwise convergence generalized for metric spaces. So basically the only difference here is that instead of talking about convergence in R here, this just gets replaced with convergence in the metric space. And now this second type of convergence is uniform convergence. So uniform convergence, I think this only applies to real valued functions. Okay, so uniform convergence means we need the maximum the difference between two functions to get closer as we increase k. So we can express that like this. And now, before we go on to an example question, there's also the LP norm convergence. So, sorry, my pen is being weird. Okay, hopefully now it's fixed. No, it's not. Okay, now it should work. Okay. So, LP norm convergence basically means the functions converge in the LP norm. So if we have a sequence of functions from a closed interval, I think this is also continuous. Then this converges in LP to some function f if the integral of this goes to 0. Okay, and one more thing before we do the example is the relationship between the norms. So uniform convergence implies pointwise, and this also implies convergence in LP. So for the LP norms, we have a relationship between different LP norms. So if it converges in a larger power, so a larger p, then it also converges in a smaller p. So this is true if p is larger than q. And uniform convergence here is basically convergence in L infinity. So this implies any LP norm convergence. But there's not much relationship between pointwise and LP convergence. Okay, now let's do the first example question from the 2016 exam. So we have a sequence of functions defined like this, and we want to discuss the pointwise and uniform convergence of this sequence. So let's start by drawing out what this function looks like. So if we ignore this domain for now, this function ends up looking like 1 here, and then it oscillates and gets smaller as it goes away from the y-axis. So here we're only interested in the 0, 1 part. So okay. I'm actually not sure where this root is. Oh, it's probably just at pi. So we're interested in this section. So this is sine x over x. So what happens as k gets larger is that this thing gets, the function gets pushed towards the y-axis. So we end up with something like, so now we only care about 0 to 1. It will end up looking something like that. So let's talk about pointwise convergence first. So at 0, the limit has to be 1 because all of these fk of the zeros is 1. And now for values not including 0, we can use a pinching argument to show that it converges to 0. So the pinching argument is basically sine of kx is less than 1 and greater than -1, or equal to. And then dividing this by kx, we get this relationship. And as k gets larger, both of these go to 0. So this should also go to 0. So that's how we get this as our pointwise limit function. Okay, now we want to talk about uniform convergence. So a property of uniform convergence is if I believe this should be a sequence of continuous functions. So this should be continuous. If a sequence of continuous functions converges uniformly, then its limit is also continuous. So here, our fk's they are continuous, and we know this because the limit of my pen is bugging out again. I'm gonna take a moment to fix that. Okay, now it should be good. Okay, where were we? Okay, yeah. So we had this, and something else to note is that pointwise and uniform limits of a sequence of functions will always be the same if they both exist. So uniform implies pointwise. That direction is clear to see, and if we have something converging pointwise and pointwise to I'll make a side note here. So pointwise, it converges to some f, and uniform converges to some g. Then if these are different, there'll always be some point between these that don't agree. So the maximum difference won't go to 0. So based on that, what we know is that if this converges uniformly, it has to converge to this function too. But here the limit has to be continuous, and this is clearly not. So that means this sequence of functions does not converge uniformly. So this property is quite useful for proving that a sequence does not converge uniformly. Okay, so here we conclude that it converges to this function pointwise but not uniformly. Now we move on to series of functions. So here there's a few theorems. The first one is the Weierstrass M-test. And this is a special case of another more general theorem. So that theorem is in a Banach space E. And if we have a sequence in that Banach space, then if the sum of the norms from 1 to infinity of that sequence converges, then the sum of the elements also converges. So here is just that applied to continuous bounded functions under the infinity norm. I should use this notation instead. Okay. Yeah, so if we have an upper bound for every single function in this sequence, and the sum of those upper bounds converges, then the sum of all the functions also converges, and it converges uniformly. So to actually see if these converge, we can use some convergence tests from like 1B calculus, and these are the ratio test and roots test. And in our next example, in our next example here, we'll actually do this with both of these tests. Okay, so next example question from the 2022 paper. We have a sequence of functions defined like this, and we want to prove that this series converges uniformly to a continuous function. So uniformly to a continuous function is kind of a hint that the Weierstrass M-test could be useful. So we try to use that here. But to use that test, we need upper bounds for every one of these functions. So this slide is basically finding that upper bound using calculus. So it's continuous and positive. So the only points where it could reach its max is its turning points and its endpoints. And it turns out that the max happens at t is equal to 1. So we take these as our upper bounds. Our next task is showing that this series converges. And here is where these tests come in useful. So first we'll show it with the ratio test. So if we take the ratio of consecutive terms, we see that it's equal to this, and we're interested in the limit superior of this sequence. But we can see that this will, regardless of what k you take, this will always be less than 1 on e. So this definitely holds, and this ratio, the absolute value of this is always less than 1. So by the ratio test, this series converges. And now using the next test, so it's the root test, we can calculate this, and we find that that's equal to this here. So that's 1 on k to the 1 over k. Then so here I am a little bit like I'm trying to understand how this turns into this. 1 on ek, 1 to the k. I think this should go on the denominator instead, so then this might have been a typo, but in either case, I think this still does hold. Yes, so in yes, from this line, this definitely should be on the denominator, or it should have a -1 here. Then here we have the limit superior of this sequence is also less than 1. So we can use the RIZZ test to conclude that this series converges. And once we have shown that this series of this series of upper bounds converges, we can conclude from the Weierstrass M test that the series of functions converges uniformly to some continuous function. Okay, the next section is a few theorems on differentiating and integrating limits of sequences. So here we have a sequence of functions that are continuous and defined on 0, 1. So this can actually be any closed interval AB, and these will still hold. So if all of these functions are differentiable and converge uniformly, and the derivatives are continuous and bounded, and they also converge to something uniformly, then our limit function is differentiable, and its derivative is the limits of the kth, the derivatives of the fk. And this second one is about integrating limits of sequences. So if we have a sequence that converges uniformly, then so that implies convergence in L1. So that implies this. And here that also implies, so from that we can conclude that this limit also holds. Okay, and the last theorem of this topic is about power series. So if we have a power series that converges on some disk, then we can actually differentiate that function on that disk, and its derivative is just the derivative of this term by term. Okay, so these last three theorems, they aren't tested by themselves much, so we won't do an example on those. Our last example for this topic is more like a typical exam question for this topic. So here we have a sequence of functions, and we want to talk about the convergence of this sequence as well as the convergence of this series. So let's draw a diagram of what a pen is lagging out again. I'll just start using my mouse. So let's start by seeing what these functions look like. So if we plot them, and when n is 1, we have a spike of height 1 between 0 and half. Oh, that's a bit big. Okay. When n is 2, this is between half and 2/3. So it's something like that. And the height is half, and so on. So the next spike starts when the previous one ends, and it gets smaller every time, and so on. So point-wise, we can guess that this should converge to 0. So here we can basically push this spike as far to the right as we want, and then for any points we can show that eventually that becomes 0. And the endpoint, so at 1, it's for any finite n, 1 will never be inside one of these intervals, so it'll always be 0 at 1. So here, okay. Okay, it seems like I lost connection briefly, but now I'm back. Here, okay, so we just did pointwise convergence. Now we'll talk about uniform convergence. So usually when we saw spikes, it was that the spikes were connection getting larger and larger. So although we had pointwise convergence, we didn't have uniform convergence. But here the spikes are just did pointwise, getting smaller and smaller. Now we'll talk about uniform convergence. So usually when we saw supremum of the difference between each of these and 0 is the height of the spike, 1 on n. And as we increase n, that goes to 0. So we can conclude that this sequence converges uniformly to 0. Okay, now we talk about this series. So this series is we add all of these together. So if we just try adding these together graphically, we can see that this should just be all the spikes on one graph. So it will look something like this, with the spikes getting smaller and smaller. And on this slide, we kind of want to find a way to express this kind of taking every spike and putting them together. So we introduced this term. So we introduced this term active. So basically, if so at every x, we just take the fn such that this x value is in this interval, so it's part of a spike. And here, a side note is that we can't use the Weierstrass m-test, since if we do, and we take all of the upper bounds, we have the sum of 1 on n, which diverges. Okay, so based on this intuition, we have a limit function. Now we just have to justify that, justify why our series converges to that. So point-wise, if we want to match a certain point, we can just take n large enough so that the spike including that point is included, and then that would satisfy point-wise. And uniformly, if we have any, say, epsilon that we want the difference to be smaller than, we can just take spikes until the last spike until the first spike that's not included has height less than epsilon. So that's why this also converges uniformly, and the details of the proof are here. So this is like formally defining our limit function, and here is talking about the uniform convergence. So after that, we can conclude that this series converges both pointwise and uniformly to this function we define, which is the sum. So it's a function including all of the spikes. And that brings us to the end of this question, and also the end of the first half of this seminar. The next half should start at 3, I think, and it will cover the rest of the topics. Okay, thanks for watching, and hope to see you back for part 2.